Hey, welcome. Have you ever just stopped and looked at the world through the lens of physics? It's pretty amazing. You start to see that everything is just a collection of really cool puzzles, where things like motion and speed all follow these beautiful, elegant rules. And today, we're going to put on our physics hats and solve one of those absolute classics.
I mean, really think about that for a second. If you're just standing still on the shore, the wind you feel is, well, it's the actual wind, right? But what happens when you're on a ship that's cutting through the water? All of a sudden, the wind you feel on your face is this mix of the real wind and the wind that your own movement is creating. It's all about relative motion, and trust me, it's way more interesting than it sounds.
Okay, so let's get into the nitty-gritty. This is problem number 1.6 pulled straight from a legendary physics textbook by Irodov. It's a classic for a reason. So our mission, should we choose to accept it, is to figure out not just how fast the wind feels to someone on that ship, but also what direction it seems to be coming from.
All right, so to solve this beast, the very first thing we have to do is break down all the information we've been given into clear, simple pieces.
So here's the game plan. We need to get a really good handle on what we know and what we're trying to find. We've got the true speeds and directions for two things, the ship and the wind, both measured from a fixed point, like standing on the ground. But our goal is to find the wind's velocity from the ship's moving point of view. That's the key.
Now, before we can even think about plugging in numbers, we need a key to unlock this whole puzzle. And for this one, that key is the fundamental idea of relative velocity. In plain English, it's all about perspective. It's the answer to the question, how fast does it look like object A is moving when I'm standing on object B, which is also moving? Your own motion completely changes how you see the world moving around you.
And here it is. This one little formula is the absolute heart of our entire solution. It basically says that the wind's velocity relative to the ship is what you get when you take the wind's velocity vector and subtract the ship's velocity vector. And see those little arrows over the V's? They are super important. They're reminding us we're dealing with vectors, which have both speed and direction.
So, now that we have the formula, our next step is to turn all those words from the problem into a picture. A vector map is going to help us really see what's going on here.
First things first, every good map needs a compass, right? So we'll set up a standard XY coordinate system. We'll say the equator, running east-west, is our x-axis, and we'll make east positive. Then, the north-south line will be our y-axis, with north being positive. This just keeps everything nice and organized.
Okay, now we can actually place our two vectors onto this map. The ship is the easy one. It's moving straight east, right along our positive x-axis. The wind, that's a little trickier. The problem says it's coming from the southeast. And this is a classic trap. If it's coming from the southeast, that means it's blowing towards the northwest at that 60-degree angle.
All right, our map is all set up, our vectors are defined, so it's time for the math. Now, trying to subtract those angled vectors directly is a real headache, but if we break them down into their simple x and y parts, their components, it just becomes basic addition and subtraction. So much easier.
This table really lays it all out perfectly. The ship's velocity, that's all in the x direction, nothing in the y. For the wind, we just use a little bit of basic trigonometry, cosine for the x component and sine for the y. And notice how the wind's x component is negative? That's because it's blowing west. After that, it's a piece of cake. We just subtract the components, x from x and y from y.
So this is our final x component for the wind we feel. And that negative sign tells us everything. From the ship's deck, the wind feels like it's blowing hard to the west. The ship's own eastward speed gets slapped right on top of the wind's natural westward push, making it feel way, way faster. And here's our final y component. It's positive, which means the wind feels like it's blowing to the north. So let's picture this. If you were standing on that deck, you wouldn't just feel a breeze from the side. You'd feel this powerful gale that seems to be pushing you both north and west at the same time.
Okay, so we've got the components. These are the building blocks of our final answer. Now let's put them back together and find out the final speed and direction, what you would actually experience on the ship. So, to get the overall speed, the total strength of the wind, we just need to combine our westward and northward components. And the Pythagorean theorem is the perfect tool for this job. You can just think of our two components as the sides of a right triangle. The hypotenuse of that triangle, that's going to be the speed we're looking for.
And there it is. Look at that. To a person standing on that ship, the 15-kilometer-per-hour wind actually feels like it's blowing at almost 40 kilometers per hour. That is a huge difference. It feels so much stronger because the ship is basically driving straight into the wind's westward motion.
But wait, speed is only half the story, right?
It's a vector. We also need to know the direction. And for that, we turn back to our old friend, trigonometry. The arctangent of the y component divided by the x component will give us the exact angle of this new relative wind.
The math spits out an angle of about 161 degrees. Now, if we measure that from our positive x-axis, which was east, an angle of 161 degrees points up and to the left, which confirms our wind is blowing towards the northwest. So to any sailor on that ship, this is a strong northwesterly wind.
So what's the big takeaway from all this? Well, first, breaking down complicated vectors into simple x and y components is an absolutely killer problem-solving tool. And this method doesn't just work for ships. It's the same math for a pilot flying in a crosswind or a boat trying to cross a river. But the biggest idea here is that in physics, your frame of reference, your own motion, changes absolutely everything you see.
And that kind of leaves us with a final thought to chew on. Think about walking in the rain. Why do you automatically tilt your umbrella forward, even if the rain is falling straight down? Or what about trying to throw a wadded-up piece of paper into a recycling bin on a windy day? Our world is just filled with these hidden vector problems. So where do you see relative velocity at play in your life?